So this is a fairly tricky question. The first one is actually not true. The reason it's not true is there's no guarantee that the same ciphertext with different keys doesn't decrypt to the same message. So we know that the size of M0 is no bigger than the size of K because we constructed by unioning the decryption, which produces just one result over all possible keys. We know that it's no bigger than the number of possible keys. We don't know that it's actually equal to that. That would require another assumption about the decryption function. The other two properties we do know are correct. So we know that M0 has fewer elements than M, and this is the case because of this assumption that we said that the space of possible messages is greater than the space of possible keys. So if that's the case, combined with the size of M0 being less than or equal to K, well, then we know that the size of M0 must be less than the size of M. The third property is also true, and this is the key property that should give us the insight why it can't be a perfect cipher, is that there exists some message in M that can't be in M0, and that follows directly from this property. If one set is bigger than the other set, there must be some element in the bigger set that's not in the smaller one. So how do we go from there to prove that it's not a perfect cipher? Well, let's remember our definition of a perfect cipher, and that was that the probability that the message is some particular message, given the ciphertext, without knowing anything other than that ciphertext, is equal to the probability that M star was the message beforehand. That probability hasn't changed. In this case, well, if we have intercepted C0, this was our ciphertext for the example, well, because of this property, we know that the probability that the message is M star is actually 0, because that's not in the set of possible decryptions of C0 over all possible keys. But we said that M star was a message in M that initially had some non-zero probability, which is not the case that these two are equal, because this was greater than 0. So we've contradicted the requirement for a perfect cipher. The only assumption that went into this was this one. We assumed that there existed a perfect cipher where the number of messages is greater than the number of keys. And we've reached a contradiction. So this proves that there exists no perfect ciphers where the number of messages is greater than the number of keys. So this is bad news. Every cipher that's practical must be imperfect. So this means that given some ciphertext that an attacker intercepts, even if the attacker knows nothing about the key, they can eliminate some of the possible messages. So this means when people attempt to use ciphers similar to a one-time pad in practice, they tend to actually not work very well. And the reason for this is that they reuse keys because the number of messages they want to encrypt is greater than the number of keys they have. Next, we'll look at an interesting historical example of this.